Hello, my name is Garrett Mitchener, and I'm in the math department at the College of Charleston, and I'm going to be talking about ranking with Hamiltonian dynamics. Let me begin by saying what I mean by a ranking problem. I'm going to suppose that I'm given a list of items, x sub 1 up to x sub n, and I'm given pairwise comparison data. That takes the form of a matrix big W, and each entry W sub jk indicates how strongly x sub j should be placed before x sub k. So the idea is that generally these wjk's are positive, and larger values mean that the data is more confident that item k should be ordered after item j, or item j should be ordered before item k. Formally, we're looking to put these items in an order that is as consistent as possible with that given information, and that takes the form of a permutation that puts the items in that order. Now, as to what exactly does it mean to be as consistent as possible with W, well, that's kind of a fuzzy concept, and this is where the data science and machine learning comes in. Um, if you're given contradictory or incomplete information, what do you do? So that's kind of the challenge of these problems. Um, Now, as to how do you solve these, well, if you've only got a few items, you could just look at all n factorial orderings of those items and pick whichever one you like best. For large values of n, though, actually that becomes impossible very quickly. Um, if you've got some additional information, sometimes there are heuristics that allow you to come up with reasonable orderings uh, relatively quickly. More formally, there's a lot of research into using integer programs. So for one of these, you would specify some uh, some quantity to minimize or maximize, say minimum violations of some intuition of ordering, or maximum harmony with the ranking matrix, with the comparison matrix, and then you use the constraints to specify that you'd like for the ordering to be transitive and antisymmetric, for example. Um, from the data science community, there's an algorithm called rank boost, which is related, of course, to boosting. This does a reasonably good job and is actually very flexible. Um, but what I'd like to do is to consider the possibility of using dynamical systems to solve ranking problems, and I'm interested in that for several reasons. So on the one hand, I would like to develop practical algorithms and also some theory for solving ranking problems. I'd also like to develop a notion of rankability. That is, given this data and given that an algorithm has produced a particular linear ordering, how confident am I of that ordering? How useful is it for producing predictions? Do I believe the ordering? Um, and is there a way to tell ahead of time that this set of data is going to yield good rankings, or is this data going to be problematic? But a third goal is to develop interesting dynamical systems. So not only am I interested in the data science aspects of this, but also maybe there are dynamical systems that have something to do with ranking, and we can use knowledge from data science to understand how these dynamics work. So to begin, my approach is to define some sort of ranking potential. Here's the idea. I'm going to put the items on a real line and say that there's a particle for each item somewhere on this real line, and they exert forces on each other. When the given pairwise comparison data says that, say, item j should be before item k, then there should be some kind of force between items j and k that pushes j to the left and k to the right. And it's asymmetric in that if particle j is already to the left of particle k, then this force should be rather low. But if the two particles are in the opposite order, then the force should be strong. So then if the comparison data has some sort of contradictory information in it, the forces will have to be balanced out somehow or another, and the dynamics will change depending on how that happens. The particular form of the ranking potential is this linear combination weighted by entries in the comparison matrix of these exponential terms. Again, the exponential terms are there to represent the fact that if item j is supposed to be to the left of item k, then this difference will be negative, which means that this exponential term will be a small magnitude positive number, which contributes very little to the energy. Whereas if the two particles are in the opposite order, then this difference will be positive, and the exponential term will be a large magnitude positive number, high energy. I'm going to use q sub j to represent the position of particle j. The gamma r is a scaling parameter that it basically allows you to define units. And I've put the elements of the comparison matrix here. There are other places that you could put them. For example, you can actually move them up into the exponent. The idea here is that wherever you put this, a larger value of W should go along with greater emphasis on getting the ordering of these particular items correct. And as I've written it here, if there's no information given about a comparison between items j and k, then the corresponding W will be 0, and that term will be zeroed out and have no influence. So that's dynamically where the ranking potential comes from. In terms of data science, you can also interpret this as an empirical risk function, and the terms on the right-hand side here are essentially loss terms. Exponential loss functions like this are used in a number of statistical learning theory applications, which is why I've chosen this particular form to use in the dynamics. Now, there are lots of different dynamical systems that you could build from that ranking potential. In fact, it makes sense to just do gradient descent on that ranking potential in some cases. The dynamics in that case are not terribly interesting. You just go to the bottom of whatever potential well you happen to start in. So I decided to investigate what would happen if I used Hamiltonian dynamics. To make this a little more reasonable, I introduced a confinement potential, which effectively puts each particle in a well like this. You could use a parabolic well. I used a Koch well mostly because there are exponential functions floating around, and I just decided to try Koch instead, expecting that magnitudes of everything would work out nicely, and there may be some good theoretical results that come from a Koch-shaped potential well. Now, just the confinement potential alone essentially creates a set of oscillators. Then the ranking potential can be interpreted as coupling terms between those oscillators, so that rather than have all the oscillators going back and forth right there at the bottom of the well, you might have a particle oscillating over here and a particle oscillating over here, because there's information that particle J should be to the left of particle K. So that's another dynamical systems way of interpreting this confinement potential. So next you build a Hamiltonian by adding the confinement potential and that ranking potential from the other page. This term is just a kinetic energy term, nothing too crazy there. The p's, of course, are the conjugate momentum variables to the q's. Returning to uh, the statistical learning theory approach, there's always a trade-off between solving the problem precisely and having some kind of regularity or generalization capability in the solutions. For this kind of problem, it makes sense to impose regularity by saying that we don't want the particles to escape to infinity. And that's what this potential well does in the language of data science. It regularizes the solution by keeping the numbers from getting too large, and there's a balance between them. I've chosen to do that by putting scaling parameters on the confinement potential and the ranking potential, so that way I could leave the kinetic energy term as just plain 1/2 sum of momentum squared. So the end result of this now is this Hamiltonian, and of course you can use the Hamiltonian equations of motion to now have a dynamical system, and it will conserve energy and have other geometric properties. Another reason for choosing the particular form of ranking potential that I did is that the Hamiltonian that results actually has a nice connection to the Toda lattice. The Toda lattice is a well-studied integrable system, and I'll say in a minute exactly what that means. Basically, if you line up the items in just a plain old chain where there's an item on the left and then an item immediately to its right and one item immediately to its right, you get a band diagonal matrix for the comparison matrix with ones on the one diagonal above the main diagonal. The nice thing about the Toda trajectories is that the particles sort of come in and scatter off of each other in a perfectly reasonable order. So whatever particle is, no, sorry, that's in the wrong place. Whatever particle is leftmost comes in from the far left and bounces off the others and then continues back to the far left. And then whatever particle is to the far right comes in and eventually comes out on the other end going to the right. In between, the particles can change positions and pass through each other. Contact between the particles is not considered a collision of any kind. They're allowed to freely pass through each other. And these solutions are generally well behaved. So having said all of this, it was one of my colleagues, Annalisa Collini, who noticed that the Hamiltonian that I had written down resembled the Hamiltonian of the Toda lattice. And so I spent some time trying to see if there was a way to generalize the Toda lattice to something that looked more like a general ranking problem where maybe you can be given contradictory information. So this is a sort of trivial ranking problem. All the items come in an obvious order and there's nothing interesting going on. So is there a way to generalize Toda dynamics in a way that admits more interesting ranking problems? So to attempt to do this, the best approach that I found was to do a change of variables. So with this, you incorporate the dynamics into these new variables, resulting in, again, a band diagonal matrix that I've called big A and a diagonal matrix that I've called big B. There are actually a couple of different ways of doing this. I've selected this one because after a lot of trial and error, this was the closest thing to being able to generalize the Toda lattice to a ranking problem. So what you can see here is that this B is a rescaled and opposite sign momentum, and the A's, which I've written using this notation, are basically just the force terms between two adjacent particles. Once you've done Flaska's change of variables, you can define an L matrix and an M matrix like this. So L is A plus A transpose plus B, M is A minus A transpose. L is symmetric and M is skew symmetric. And when you work out what happens to the differential equations for P's and Q's, when you translate that into dynamics for the A's and the B's, you get something called isospectral flow. So that is that L dot is equal to ML minus LM, which is the commutator between the matrix M and the matrix L. And L and M form a lax pair. What this gets us is that, so isospectral flow has the property that the eigenvalues of the L matrix are conserved. They're constant over time as the dynamics move. And that's what it means for the total lattice to be an integrable system. There are other definitions of an integrable system. This is what it means in the case of the total lattice. So what could we possibly do to generalize this so that we could have a weight matrix that's more general than just a chain? Okay, well, I've tried a lot of different things. The key to this is that the Hamiltonian that you get for the total lattice looks like this. And in the case of this band diagonal weight matrix for a chain of particles, it turns into this, which is very much like what I was starting with in formulating the Hamiltonian a few pages ago. So what I'm going to do is try to sort of generalize this and see what happens. It turns out, again, after a lot of trial and error, that taking a weight matrix and splitting it up so that the upper entries, so the upper triangle entries appear as real elements in this A matrix, and the lower triangle appears as these complex elements. You can form this matrix A. It's an upper triangular matrix of complex numbers. B, I'm leaving the same. An unfortunate consequence of this is that there's not really a way to go back from this picture to particles, because there's sort of more of these A elements than you can really do particles for. So we're giving something up by passing to this dynamical system. Again, I'm going to define L and M matrices, and in this case I can enforce isospectral dynamics. So again, why that particular A and B? Well, you have to give up on the P and Q variables, so it's not clear how I'll be able to interpret this. Importantly, the trace of L squared is still conserved, and it has this form, only now there are a lot more of these W terms that are non-zero. So again, there are many more terms in this energy function. And by the way, part of why trace of L squared is important is, of course, that if the eigenvalues of L are conserved, the eigenvalues of the square of L must also be conserved. They're just the squares of those original eigenvalues. The trace is the sum of eigenvalues, so trace of L squared is the sum of the squares of the eigenvalues of L. So this is something that's conserved under isospectral flow just because it's a function of the eigenvalues of L. So this is looking reasonable. Also, the dynamics that you get out of this are independent of renumbering. So if you were to renumber the items, you would get the same thing here, and the dynamics would just be renumbered as well. So that's an important feature. There are some drawbacks though. For one thing, it is known that total dynamics are essentially equivalent to a sort of continuous time QR factorization. And what happens is that the off-diagonal elements of L, the AJKs, converge to 0 as time goes forward. The B's, which are the diagonal elements of L, converge to the eigenvalues in increasing order, or you can run time backwards and get the other order. And there just doesn't seem to be any ordering information preserved by this dynamical system. So as far as I know, it is possible to generalize totodynamics from the original chain and to sort of try to do this ranking problem form. That kind of problem has been studied in the integrable systems literature, but unfortunately it appears that the ordering information is kind of wiped out. I could be wrong about that. I would love to know if there's something that I've missed, but as best I can tell, all ordering information of the individual items disappears asymptotically as time goes to infinity. To do a more thorough test of these algorithms, I decided to construct some synthetic data. So here's some of the details about how this was done. So imagine that you've got 20 teams and they each play each other in a tournament. So each plays all of the others. The winner should go to the right, and the loser goes to the left. I want a random element, so it is possible to have upsets. But I want to have control over how many upsets, and I want to still have some kind of underlying linear order to pull from. So here's how I set that up. Each of the 20 teams has an underlying strength that's a real number on the real line. And this represents a sort of ground truth. Then, to play the tournament, I pick two teams, J and K, and the outcome of the tournament is determined by this number. It's a probability between 1/2 and 1 that indicates that team J should lose to team K, and so J goes on the left and K goes on the right. To explain this probability, if S sub J is less than S sub K, that means team J is weaker and team K is strong. This difference will come out negative. I multiply by a positive beta that gives me some control over the overall probability of upsets. And this number will come out to be rather small. So when you do this division, the result will be a number close to 1. So when S sub J is less than S sub K, this happens with high probability. And what that looks like in the W matrix is that you set W sub Jk equal to 1 and W sub Kj equal to 0. And so with some small probability, you get an upset and the 0 and 1 are reversed. For low values of beta, the effect here is sort of muted, and you're more likely to get upsets. In particular, if beta is equal to 0, then when you work this out, you get that the probability that J comes before K ends up being just 1/2. So if beta is equal to 0, then all teams are effectively are effectively the same. And if beta is large, then there are essentially no upsets. So vanishing probability of upsets. The advantage to using synthetic data is that I have ground truth, and I can look at the result of a ranking algorithm and see how far it deviates from the actual ground truth. Some of that will be due to limitations of the algorithm, and some of it will be due to noise in a particular sample. So to do this random test, I create 10,000 samples using a particular set of strengths and a particular beta, and try all of the ranking algorithms that I'm interested in with various parameter settings on the same 10,000 samples. And now I can do pairwise t-tests to see, does one algorithm give consistently better results than the other, or are they about the same? Okay, so let me show you what strengths I'm going to talk about first. So if you simply put the items equally spaced on the number line with S1 at 1 and S2 at 2, so that there's 1 unit of strength in between each, that should be a nice, easy ranking problem. There's no question of which items should go in which order. And so that's the data that I'm going to talk about first. I'll get to this in a later slide. Okay, so now we've got these sample problems. We can run the ranking algorithms. How do we evaluate the orderings that come out? Well, there's at least 3 different ways that obviously should be tried. One is that I can look at the ranking potential for the position vector that actually comes out of the ranking algorithm. Now, this is only valid for the methods that I'm talking about that come from Hamiltonian dynamics. I'm going to compare them to rank boost, but rank boost doesn't give the same kind of position vector. It does actually give a position vector, but it's on some other scale. So I can't really talk about, it doesn't really make sense to talk about the ranking potential of that. A more universal way of evaluating a ranking is something called the tournament score. The way this works is that you start with the original weight matrix, and for the most part, there will be ones scattered throughout this matrix. But if you use a permutation to sort the columns and rows, if you can do that effectively, then most of the ones will end up in the upper triangle, because what that means is that low-numbered items are appearing before. Sorry, a low row number gives an index that should appear below a higher, or to the left of a higher column number. And so in some sense, a ranking problem amounts to sorting the rows and columns of the weight matrix to push as much of the mass into this upper triangle as possible. So the tournament score is just the sum of the weights that have ended up in the upper triangle in this reordered matrix. In fact, if you're using one of the integer programming algorithms, one way to set that up is to use the tournament score as your quantity to optimize, and then you use integer linear constraints to enforce transitivity and so forth. Another way of evaluating an ordering that is particular to the synthetic data that I'm using here is inversion count. Since I'm using synthetic data where I know that the items should be ordered in a particular way, just 1, 2, 3, 4, up to 20, um, I can look at the ranking order that comes out and see how far does it deviate from 1, 2, 3, 4, 5, and so on. And an easy way to do that is something called inversion count, which is how many swaps does it take to bubble sort the resulting permutation. So, for example, if I had 4 items and my permutation gave the ordering 1, 2, 4, 3, well, there's one swap here to get it into the correct order 1, 2, 3, 4. So for this, the inversion count is equal to 1, whereas if I had 1, 4, 2, 3, I would have to swap the 4 and the 2, and then swap again, and so that would give me an inversion count of 2. And if I had 1, 4, 3, 2, then I would have to first swap the 4 here and then here, and then I would have to swap the 3 and the 2 again once they're in place. So that would give me an inversion count of 3. So this gives a way of seeing just how far does this deviate from the intended correct ordering of the items. So here are the results. So first I'm going to show you the ranking potential. Lower ranking potential should be better. Again, 10,000 random samples, linear equally spaced strengths, and I set beta equal to 0.5 for this round of tests. So there are some upsets. You take the ranking potential that comes from finding the point on the trajectory that minimizes r, and compare that to the position vector that comes from the average integral over the trajectory. And you subtract those, again, subtract result of the first algorithm on the sample and the second algorithm on the same sample, and look for a 95% confidence interval. The numbers here are comfortably away from 0. So what that means is that the values of r that are coming out of the trajectory minimum are less than the r that comes out of the average integral. So in this measure, the trajectory minimum is giving better results. But of course, things start to get complicated. If you start looking at tournament scores, again, that's how much of the mass is pushed up into the upper triangle of the matrix once you resort the rows and columns. High tournament score is better. Again, same 10,000 samples, subtracting the tournament score calculated using the ordering from trajectory minimum r, subtract off the tournament score calculated from the ordering from the average integral method, and you can see that this is comfortably negative. That means that the average integral method is actually giving slightly higher tournament scores. So according to this measure, the average integral method is slightly better. As I said, I'm also interested in how this compares to a standard algorithm like rank boost. So if you calculate tournament scores comparing trajectory minimum r to rank boost, this comes out comfortably positive. That means that the trajectory minimum r is actually giving slightly higher tournament scores than rank boost. And the statistical test is transitive. The average integral method is giving slightly better results than rank boost. So in this case, from strongest to weakest, the average integral method is strongest, and rank boost is ever so slightly weaker. We can also look at inversion counts. Lower inversion counts mean stronger. So by this measure, again, the same kind of comparison, it turns out that the trajectory minimum r method is best. The average integral method is a little bit weaker, although not by much, and rank boost is just a little bit weaker than that. Now, these numbers, I should point out that these are statistically significant, but they aren't huge numbers in the context of these problems. So it's not a matter of that one of these methods is far better than the others. They're of comparable quality. which is kind of reassuring because rank boost was sort of specifically designed with a data science use in mind, whereas the Hamiltonian mechanics was designed to also give interesting dynamics. So it is kind of nice to see that the rankings that come out of this are competitive with rank boost. I should also point out that even just saying is one of these algorithms weakly better than all of the others overall is not really possible. So if you increase the probability of upsets by lowering beta, you get slightly different results. Trajectory minimum R achieves higher tournament score and lower inversion count. But when you decrease the probability of upsets, rank boost achieves a lower inversion count. And so it's the three algorithms are roughly comparable. None of them is clearly better than all of the others in all situations. Now I want to say a word or two about rankability. This was actually the conversation that got me started on this project. The idea was to be able to look at data and see how well does a linear ordering actually represent this data. If we get a linear ordering out of some algorithm, how confident do we really believe the results? And at the time that we were talking about this, it looked like the only thing you could do was run your favorite ranking algorithm, and if the output made sense, then your data was rankable. We are still working on an algorithm-independent way of talking about rankability. But just to give you a couple of things to look at, this is a complete directed graph so that everything is every item is interchangeable with every other item. And there are cycles all over the place. So these are 6 items that are essentially indistinguishable. So you can run any ranking algorithm on this, and it will give you an order, but the order is sort of inherently meaningless. Any order that you could choose would be consistent with this data because it's inherently unordered data. On the other extreme, here I've got a complete tournament. It's a little bit harder to see because I've drawn it as a circle for compactness, but this one should go to the farthest to the left, and then 2, and then 3, and then 4, and 5, and 6. And you can tell, for example, that 6 is the strongest because all of the arrows are coming into 6, and that 1 is the weakest because all of the arrows are going out of it. This is sort of the most rankable case where the data is absolutely clear that this is the correct order for these items. And then you get these intermediate things, like this example in the middle is partly rankable and partly not. The rankable part is that there are 3 items over here and 3 items over here, and all of the arrows from a yellow item to a blue item are facing this way. So all of the blue items are stronger than the yellow items according to this data. But then within the blue items, all 3 of those are interchangeable. And within the yellow items, all 3 of those are interchangeable. So in this case, we should believe rankings that place 1, 2, and 3 to the left and 4, 5, and 6 to the right. But other than that, any information that 1 should come before 2 is probably just noise. It's excess precision, if you will. So how would you go about doing rankability? In the case of an algorithm based on an integer program, you may not be able to look at the variables in their optimum state and make any sense out of how much confidence you should have. But with these particle-based methods and also with rank boost, not only are we given an order, but the particles or the objects are put in some kind of position. And so for this 2 groups example, you would expect 1, 2, and 3 to be over here close to each other in some order, and then 4, 5, and 6 over here in some other order with a big gap in between them. And that gives you some understanding that you've got a group over here and a group over there, and within each group the ranking is not really well defined. But between the groups there is there's definitely a strong group and a weak group. So as to how do you tell how rankable something is using one of these Hamiltonian algorithms? Well, a simple way to do this, looking again at the entire data set all at once, is to look at what I've taken to calling the spread, which is the leftmost particle minus the rightmost particle. And in this, I'm assuming that I've just picked two symbols there. This is an example that we looked at before, where there was a group of 3, and again these are in a cycle and they're indistinguishable, but then there's this 4th item that is weaker than item number 1. And what you can see is that again here these are the particle positions for the minimum value of r along this trajectory, and what you end up with is 4 is over here on the left somewhere, and then 1, 2, and 3 are in a clump over to the right. So there's the clump. If you look at it from the average integral perspective, the average value of Q4 is somewhere down there, and the other 3 particles are oscillating up there somewhere. And whatever that distance is would be the spread for the average integral method. Now, if the particles formed a more definite line, like a chain like that, then what would happen dynamically is you can again imagine the particles inhabiting this well, and they would push on each other so that particle 1 oscillates over here somewhere, 2 oscillates there, 3 will oscillate over here, and 4 will oscillate over there. So Q1, Q2, Q3, Q4, and then this is that Koch potential. And so you will pick out a rather long spread because the particles are pushing each other as far apart as possible. So a greater spread from the particle positions should indicate that the underlying data is more rankable, whereas if a bunch of them are exerting conflicting forces or no force at all, then they'll just clump together. So now let me go back to the next 2 batches of synthetic data. Same model. Every item has an inherent strength, Sj, but now instead of having nice evenly spaced, I'm going to put one group of particles at strength 0 and another group of particles at strength 1. So that should give me a clump of particles here and a clump of particles over there. And then just for reference, I'm going to do a completely unordered case where all the particles have strength 0, at which point all of the items are indistinguishable, and the particles are, they should all be clumped very tightly. Okay, here are the results. This is using the average integral method, and I've used 4 different values of beta. So this is at 1/4, 1/2, 1, and 2. The x's up here correspond to the linearly ordered, evenly spaced strengths. And as you can see here, for high values of beta, there are very few upsets. Essentially, the particles come out in order from 1 up to 20 with very little deviation, and they indeed spread out as I'd showed before. Now over here, where the probability of upsets is high, here we're seeing average, the spread is a good bit less. And that's again because when you have upsets, it creates cycles or other contradictions in the given data. And so you've got some particles that aren't pushing each other consistently. As to why am I drawing these as cross marks, really I had intended to draw 95% confidence intervals. Again, I've got 10,000 samples. I can do that. The thing is that the confidence intervals were so tight that they were barely visible, so I just plotted one endpoint. So again, it is as expected. The spread increases as you increase beta because there are fewer upsets in that linear, evenly spaced strength data. Now, for this data, that's the two groups, and that's where there's a clump of items at strength 0 and a clump of items at strength 1. And again, we're seeing that for low values of beta, there's a high probability of upsets, higher probability of getting contradictory information in the data, and the particles don't spread out as much in that case. But for larger values of beta, the particles do spread out, again, because there's fewer upsets. Now, this line is for the unordered data. So this is where all the items have the same strength. Beta doesn't matter because all the items have the same strength. The probability of upsets doesn't even make sense. Every particle is just 1/2 against all of the others. And so you're seeing a consistent low spread for all of those samples. So this is showing that the spread is actually a reasonable way to talk about rankability of these different synthetic test cases. I'm not going to show the results for rank boost or trajectory minimum because they're essentially the same, just on a little bit different scale. I thought I'd also use some real data that's got a lot of complications to it actually, and just show you what happens. So for this slide, I'm looking at the National Football League. So this is American football, not soccer. And I'm looking at the 2018 to 19 season, which was not disrupted by a pandemic, but it did have some surprises in it. The structure of the NFL season is that the teams play a certain number of games. Every team plays the same number of games. They play some against other members of their conference, which is kind of a subgroup of all of the teams, and then they play some out of conference games as well. That gives point spread data from all of these different games across the season, and also so you get home versus away effects. You get the fact that football is a game where small probability events can actually be very important. So if a particular play goes especially well or especially poorly, that one play might be the thing that decides the game. A controversial call by a referee, sometimes looks like it may be the difference between which team wins and which team loses. Once the regular season is done, there's a tournament, the playoffs, that eventually ends up in the Super Bowl. It's a single elimination tournament that boils down until there's just the two best teams. They play for the championship in the Super Bowl. So what I've drawn here is that for the teams that ended up in the tournament, I got their records from the main season, regular season, used the point spreads as the weights in the W matrix, and tried out the different ranking algorithms. In this case, I'm going to show you the average integral method results, but I got very similar results from the trajectory minimum R, and surprisingly from rank boost. They all agreed on this information. So what you're seeing here is the teams that made it to the playoffs, and I've used just 1, 2, 3, 4 as the horizontal coordinate, and then the state vector position for the vertical coordinate. So that's Q1, Q1 here, and then all the way up to Q12. A couple of things to know about this. For one thing, there is definitely a gap here. All of the methods agreed on that. Um, the other thing that I should tell you is that the New England Patriots had some unexpected, they had some unexpected behavior in the regular season. They didn't do particularly well at the beginning of the season, but then they actually ended up winning the Super Bowl. So this was a case where the regular season data genuinely was not a good source for predicting the tournament. Let me show you uh, what what this ranking gives you. So these are the playoff games, and so these are the early ones, and then down here is the Super Bowl. And this column is the actual point spreads. So actual point spreads. So for example, this means that Houston and Indianapolis played, and Indianapolis won by 14 points. This one means that Dallas and Seattle played, and Dallas won by 2 points. What you're looking at over here are the QJ minus QK numbers using the Q that's, in this case, it's QAI, the average integral. A red number means that this has the wrong sign. So if this number comes out positive, it means that the J team should be to the right of the K team. And so this is positive, and you can see that the J team actually lost to the K team. So the red entries here are the ones that are the wrong sign. The blue entries have the correct sign. So in other words, the average integral method here only got 5 of the 11 games correct. Only predicted 5 of the 11 games correctly. The trajectory minimum R method actually missed one by a tiny bit. So the the results of this are, of course, a little bit disappointing. But as I said, football is a game where a lot of complications come into play. The big one, again, being that New England did much better in the playoffs than they did in the regular season. A few things to point out are that apart from New England, the Kansas City-Indianapolis game was correctly predicted. And if you'll remember, Kansas City, that's this one that all the methods agreed was the strongest. This one was Los Angeles and Dallas. So here's Los Angeles and here's Dallas. So that actually worked out rather well. This one is New Orleans and Philadelphia. So here's New Orleans and here's Philadelphia. And finally, is that all of them? Yeah, okay. So here, so Los Angeles has 2 teams. This is the Los Angeles Chargers, and that's Baltimore. So the Los Angeles Chargers and Baltimore. So you can see that some of the results are actually very sensible. And some of the ones that are missed, like this, none of the methods was particularly complicated or was particularly confident about that one. This one they also had low confidence in. So it's not completely ridiculous, but it just goes to show that sometimes the data that you're given is just not good for making predictions, and that seems to actually be typical of football. And I've also been told that hockey is hard to predict. So, so there you go. That's a real world application of this ranking, and it shows you what's going on, and it also shows you these methods that have some sort of confidence, as well as giving you an absolute order. So now I'm going to conclude, just to kind of revisit what we've looked at. I formulated Hamiltonian dynamics with a ranking potential. That was a way of incorporating pairwise comparison data into a potential energy function, and from there you can set up a dynamical system. I included a confinement potential to keep the particles from escaping to infinity, and that's necessary to impose regularity on the data analysis that's going on. Without that confinement potential, the resulting Hamiltonian is very clearly connected to the total lattice, but unfortunately I was not able to get a good ranking algorithm out of total lattice dynamics. What I was kind of hoping was that since the total lattice is effectively doing a continuous version of the QR decomposition, maybe it would attach um, an eigenvalue to each of the items being ranked, that would then give me a way to order them. Unfortunately, since it has this property that the order of particles doesn't really matter, the the ranking information is effectively thrown away. So I'm not really sure what to do with that next. At the moment, it's just sort of a mathematical curiosity, but I got to learn something about integrable systems and the total lattice, so I consider it a good use of my time. Okay, using Hamiltonian dynamics, we're going to look for particle configurations that give a low value of this quantity R, the ranking potential. One effective way to do that is to just look along a trajectory and find the particle configuration that gives the minimum R along that trajectory. Those particle positions then tell you the relative ordering of the corresponding items. That was the trajectory minimum ranking potential method, TMR. It's also sensible to treat the particles as oscillating and to look at their average positions using an integral. So that's this average integral method. And that gives a particle configuration as well. And both of these give orderings that are comparable to what you get out of the standard rank boost algorithm. Furthermore, since not only do you get an ordering out of these algorithms, but you also get a particle configuration. You can use the spacing of the particles to estimate some measure of confidence or rankability. How sure am I that this item should be to the left compared to that item? And overall, do I believe that this linear order is somehow representative of the data overall? There's more work to be done on this, but at least with the synthetic data that I was working with, everything intuitively looks reasonable. So more work to be done on that. Let me finish by giving you this slide with my contact information. So here's my website and my email address. I should also say that part of how I got this project done was that I had partly done some of these calculations, and then I got this email that there was going to be a special issue of Physica D based on the previous conference on data science and dynamical systems. I didn't know about that conference, but I thought that this project would be appropriate for the special issue, so I submitted it and just found out that it's been accepted. So here is the DOI link for it, and here is a author sharing link. So for the next month or so, you can use that link to download the article, even if your library doesn't have a subscription to Elsevier and Physica D. I'll also post the source code to my synthetic data calculations on my website, and the the paper has a bibliography that includes references to what's known about the Toto lattice. It also includes information about rank boost, um, and kind of fits how that fits into the project. I've also done some additional test cases, on real-world data, and I also tested out a Hamiltonian Monte Carlo Markov chain method that was designed for sampling from a probability that's based on a Hamiltonian. I didn't have time to get into that, but it is in the article if you'd like to look at that. And so with that, I will end my presentation, and I hope you've enjoyed it.